Welcome back. We are back. This is number 2. Today, we are going to be learning about diaphragms. I bet you didn't know that you needed to know about diaphragms, but you do. And we're not going to talk about medical diaphragms. We're not going to be referring to the breathe in. Well, that was my lungs. Bad example. But yes, diaphragm breathing is a thing. But that's not the one that we're talking about. The one that we're talking about is the kind that nobody actually cares about. But like I said before, you guys have sponge brains, and I am supplying the liquid knowledge for your sponge brains. So we have this special new addition today to our studio here, and I'm going to use it as a tool to help you guys learn about diaphragms. Now, before we get into it, I do have to give credit where credit is due. This music is by Green Observer. If you want bomb music, you should check out the Green Observer on YouTube because he makes great music. Now, let's get right into it here, kids. So, diaphragms, right? Not talking about body part diaphragms, talking about house diaphragms. Okay. So, why do we care about diaphragms? Well, we care about diaphragms because they are a very key part of the house that nobody really thinks about. Not that anybody thinks much about house framing day to day anyway, because it just doesn't fall on them. But it is a very critical component to making sure that all of the loads that are collected by the walls and other members are distributed such that house doesn't fall down. Now, let me try to give you an example. So, well, first of all, this is our whiteboard. We got to come up with a name for the whiteboard. I'm thinking something like Deshaun. Yeah, let's go with Deshaun. So we're going to name the whiteboard over here. Move my mic. So Deshaun the whiteboard. Deshaun. And we're going to put an E on the end. Deshaun. Deshaun the learning whiteboard. Now, diaphragms, right? So let me put it this way. There's usually 3 kinds of diaphragms you're going to have in a house. You're going to have a floor diaphragm. You're going to have a ceiling diaphragm. You're going to have a roof diaphragm. Now, if you have a slab on grade concrete foundation, it's still a diaphragm, but it's just a big chunk of concrete. So we don't really design it as such. But when you're building the rest of the wood stuff, you are concerned with it. Now, ceiling diaphragms and roof diaphragms. So it basically, the diaphragm is just referring to the plane that is the ceiling or the plane that is the roof. So if we were to try to figure out what a ceiling diaphragm is, we're gonna try to explain it this way. So if I were to take a simple span beam with a block on one end, a block on the other end, spanning between the two. Got to work on this mic setup here without knocking the table over. I need to be left-handed is what I need to be. So if this beam were to be loaded from the center with a load going down, and we were to have it loaded such, it would deflect, it would take the load, it would do yada yada, right? So what if I stacked a beam on a beam? Kind of like tumbling tower, you know, you remove some blocks out of the middle, you can got this thing left over. So got one beam here, another beam here. Now they're not touching each other except for on the ends. So if I have this load here up on the top of this beam, this one, it's not feeling it. It's not doing anything. If I wanted this beam to help this beam, what would I do? Well, I could do this. I could take the same block of wood that's on the end and I could put it in between the two. So now when the top beam feels the weight of something, it's going to it's going to try to do some of the work to hold up that weight, but it's also going to push some of that weight down through this block. And that load's going to be shared by the beam below it. Now, why am I drawing beams if I'm supposed to be talking about diaphragms? Well, it's because what we're going to do here is we're going to basically pretend it's a diaphragm, because what happens is when you scale this out, it becomes a diaphragm. Now, let me go a little further. If we repeat this and, we had another beam and then, beam and then beam, right? What's happening is if we were to put blocks between, these are perfectly shaped blocks. If we were to put blocks between all of these, then what would happen is the load that's coming through this, first one is going to be transferred down and down and down and down and down. And each one of these beams is going to contribute to the first one, not, I'm going to grab a different color here. I have colors for a reason. It's going to make the first one not deflect downward. They're all going to help it out. Now, the reason I drew it this way is because I'm going to now give you the, comparison to the important part, which is the ceiling, right? So what is the ceiling made of? Oh, look, a thing to hold my markers. So if I'm going to look top-down view on the ceiling, I'm going to have a rectangle, and let's draw our ceiling joists are going to be going this direction here. Okay, so that's our ceiling. Now, remember, I'm gonna turn the direction of the force. Before I drew the force was going down on the beams. Well, now I'm gonna do this. My force is coming in sideways like that. So what's gonna happen is each one of these ceiling joists, when they're installed, they're turned in such a way that they'll bend very easily in this direction. And so what we do is, one thing you could do to try to stiffen this all up is you could add blocks. If you were, a force was exerted on this first one, what would you do to help it out? Well, you could insert a block there, and then maybe you can add one there, and you can add one there. You could go all the way down the roof or all the way down the ceiling, just depends. Now, each time you add one, the first one is going to get stronger and less likely to move, and it's going to be able to handle it without breaking or bending, really. Because a lot of times we don't want sheetrock to crack, so we don't want things to move at all, really. But that's the premise. So we ought to think about, well, why is the ceiling being pushed sideways? Why is the edge of the ceiling being pushed sideways? Well, that's because houses undergo lateral forces. And we don't want them to fall over. Therefore, the things in the house have to hold these lateral forces. So if I have a regular house, like so, with a gable, and I've got a regular, let's say, 8-foot ceiling in here, and then I've got an attic up on top. So what I've got is a whole bunch of ceiling joists going across here, like that, probably in that direction. So when the wind, for example, the wind comes and hits this building, it's going to push on this whole area, and it's going to push on this whole area. These are both flat areas. And what we are concerned with is the ceiling diaphragm. So if I've got, let's do a little cross section here. Okay, so I'm going to take a cross sectional view of this, and it would look like a wall, right? So we're going to double top plate, stud, not to scale, bottom plate. Okay, so this is the cross sectional view of the wall, and then above the the top plate of the wall is right there. Above that, you would have like the gable studs that make the gable, right? So of varying length, right? So there's the gable stud on top. So what's happening here is that stud, let's say, and this wall's got studs in it too, right? Because it's just a regular wall. So we're going to think about just one stud at a time, because that's the whole point of this. So we're going to look at this stud right here. Okay, that's this one that I drew down here. Now, when the wind blows on that wall and it's trying to push this stud over, we got a few things going on here. So first of all, the stud itself is trying to be bowed in. So you would want to select a stud that's stiff and strong enough so that it doesn't bow in. Now, what else is true? Well, for something to, I got more colors. Let's use more color. For something to bow like this, we are implying that the foundation, this is just like a beam example, right? If I got a beam between 2 points and it's got some load on it, 1 point holds up, 1 point holds up. I just turn that 90 degrees and I've got a load going this way. That means something is pushing back this way. Something's pushing back that way. Something's resisting it. Okay. So if you have a slab foundation, that's easy. Down here is just the concrete. This thing's bolted down to the concrete. It's not going to slide. It's not going to move. It's resisted down there. So what on earth is resisting it up here? Well, that is the ceiling diaphragm. I know. This is really exciting. So the ceiling diaphragm is pushing back on this wall plate to keep this wall from hinging in towards the house. Now, here's the other problem that people have when they have an attic and a gable wall like this, right? So if I were to redraw this cross section, I guess over here, move my mic. So I'm going to redraw this cross section a little bit bigger. I've got my stud in the wall below, and then I've got my top plates, and then I've got a stud for my up top, and then I've got the roof doing stuff up here. Okay. So my foundation's down here. So what happens when I got the wind force, that is the evil wind force, and it comes in here and it's trying to blow on this whole face because wind blows on surfaces and makes them get pushed. Drop my marker. So what we have here is, if I draw this with a circle in the middle, you might think, well, that kind of looks like a hinge. That kind of looks like it might rotate about that point. Should nothing hold that there? So you would be correct. The problem that happens here is, worst case scenario, that gets blown really hard and there's nothing supporting that first ceiling joist, like a ceiling diaphragm, which there always is usually. Always usually. What a word. You'd get a hinge problem. This would buckle in right here and you would have a very bad day. Likely what would happen is, if there was no wood supporting this, you'd get a bunch of sheetrock like busting and cracking and blowing in. Now, this is like a crazy wind event, right? So, you got other things to worry about. But that's a possibility. That could happen. It could happen to you. So the ceiling diaphragm is the thing that keeps that buckling in from happening. It's this top force here. So where was I going with this? Oh, right. So stick framing. So the reason we have this whole ceiling diaphragm thing going on is we handle this problem with system design. And I know, really exciting words. So system design basically means that the house is designed, the way we build houses here in America, at least, when we do stick framing, we have decreased the structural member size and increased the quantity and decreased the spacing. So what that means is, like back in the day when we were building cabins and timber frame structures and all the stuff that, people used to build, because that's, you just had big trees. This is just like, architecturally what people knew how to build. Nobody had like when we came across here to America, the engines didn't have sawmills and stuff to, cut the lumber down into small pieces. So what do? We cut logs into big pieces and put big pieces together. And that's typically referred to as timber framing. A little more complicated than that. But basically, let's take a 3D house here. So you're going to have, usually, a super simple example, you can have 4 posts, right? 4 posts that make the building, and there's one back there that I'm only going to draw part of. Okay. 4 posts, big chunky things. You're going to take some 4 big chunks of wood. You're going to slap them on top of those like that. Big chunks, yeah. Ooh, this is getting bad. This is getting bad. Okay, big chunks on top of those. And then you're going to take some other big chunks. And you're going to take those up at an angle and lean them against each other. Make some big chunky roof things. Yeah, like that. Okay. Big timber frame structure. And you're going to maybe put a big chunky one at the top for the ridge. All right. And then you might throw in some like chunky angles, right? So the chunky angles are the things that give it this, lateral strength. So the reason I'm talking about the whole timber framing is that when you have timber framing like this, the frame itself is designed with all the big chunks to resist all these lateral loads and all that stuff through all the members and their connections. But what we did is we said, well, it costs a lot and it's difficult to move and it's just like complicated to build timber structures like this. What if we started making all the members smaller, lighter, easier to work with, easier to cut? You don't need crazy big tools. And it's cheaper to manufacture this in a much larger scale. So we came up with the whole stick framing thing. Now, the problem with the whole stick framing thing is, let's take a look at this wall over here, for example. That wall is a post, some kind of ceiling thing, and then they put these little kickers in here. Now, wow, that's real straight. So the kickers, what they're doing is they are stabilizing this in the lateral direction. So something tries to rack this wall forward or backward, those are going to prevent it from happening. Otherwise, you just have a hinge up here and a hinge up here, and the shape that looks like this can very easily, if you draw it correctly, could very easily look like that, and that'd be bad. But when you put in diagonals, what you've done is you create a little triangle that basically can't change shape and stiffens it up. So if we build a wall where all of these vertical members that they used to call posts turn into studs, well, if we have a big stud wall with a bunch of studs, we're not going to add a whole bunch of tiny little blocks of wood at angles like this. That would be kind of silly now, wouldn't it? So we don't do that. What we do is we create diaphragms. So the diaphragm is the combination of the studs or ceiling joists or whatever repetitive member is in the wall doing most of the gravity bearing weight or whatever. And we combine it with usually a sheathing product. Sometimes you can use like gypsum board, but generally it's a board product. It's a big flat thing that you're going to nail to all the studs and stuff like that. So the combination of those two things makes the diaphragm. And because we can combine these multiple materials in such a way that allows them to basically work much stronger and more effective and safer, honestly, than the original timber designs, we are capable of producing houses much faster, much cheaper, and stronger, honestly, and lighter. The lighter the house is, the less earthquake problems you're going to have, for example. So we want to build things light because ultimately weight means materials and weight means transportation. And transportation, materials, weight, heavy, expensive, costs money, burns gasoline, energy prices. It just makes the economy harder to function. You got to pay more for your house. So that is like why we have the diaphragms. They exist because they are solving the lateral strength problem that didn't used to exist before with the big timber stuff. So diaphragms. Okay. Now, don't lose your train of thought, Sam. Sorry, Deshaun, I messed up your border. Okay. So we talked about like wind loading a wall that makes a diaphragm bend. We talked about how the individuals effects can add up. Let's talk a little bit about the whole sheathing thing. So I talked before about adding blocks in, right? You got a beam and a beam, you're gonna add a block in the middle. Well, that's more blocks and more wood. What I talked about was sheathing products. So instead of, taking one beam and another beam in the same volume, in the same like space, what if instead of that, we just took a flat product, set it on top of both of them, and then we nailed it in to this one, and then we nailed it in to this one. Imagine this is like your table, right? Your kitchen table, and you got a piece of wood running one length of the table, another piece of wood, another length of the table. And we take a big flat piece of oak or something pretty and set it on top of them and then nail it down to each one. Now, if you try to push this one or this one's try to, something happens to it, because its nails are, it's connected to the nails, which are connected to the oak on top, right? That load's going to be transferred back down the nails to the other one and back into the other one. So they're going to share the same, thing. If I push on this, it's also going to be pushing on that. Okay. So expanded out into, framing, we take lots of studs and big sheathing panels and we cover them up all over the wall and nail them off in certain patterns. And it gives us a diaphragm. So what if, because before we had like OSBs and plywoods, people were covering their houses and ceilings with tongue and groove or skip sheathing or various planks, basically plank designs. And you might ask yourself, well, how is it that we got out of the timber framing and we got into the repetitive member framing, studs and ceiling joists and small members, right? But we didn't have sheetrock at the time. We didn't have like engineered woods of really any kind. We just had more boards. We had 1x12s and 1x10s and 1x8s, just more milled lumber. And basically what we did is we applied the same tricks, but we just didn't have large sheet products. And sheet products make it very efficient, which is why we use them now. Costs less, but we can achieve the same result in a diaphragm with plank products too. And let me explain why. So in a sheet good, this is a big sheet, and I've got a stud on one end of it and a stud on the other end of it and a stud in the middle of it. Okay. And I've nailed this off. Okay. That's been all nailed off. That's an assembly. So if the diaphragm is loaded from the side or whatever, let's say it's, like a sheathing panel on a shear wall, top plates are pushed sideways. This whole thing's going to want to rotate. It's going to want to new color, contrast. It's going to want to rotate about this point, basically, whoop, and tip over. That's what the wind is trying to make it do when it's pushing on the top. But it doesn't do that because this is anchored down to the ground and bolted. It's actually nailed also to the bottom plate, which is anchored to the foundation and all kinds of good stuff. So they don't go anywhere. But that's what it's trying to resist when it's there. So how is it that the plank products work? Well, all the plank products are doing is they're doing the exact same thing as this. They're just small scale and repetitive. So what if we took the same sheet product and we cut a little strip off the bottom? And then we decided, you know what, one strip's not good enough. We're going to go ahead and cut it into strips like this. And then we're going to install each strip in the same place that the whole sheathing panel was. And the question is that just as strong? Well, the answer is probably no, because now you've introduced a bunch of like breaks in the plane. However, you can still add strength just like the planks do. And this is how. So in a very basic situation, we're going to have a block and a block. I could put one sheet on this whole thing, nail it to this, and then it'd have a good rigid plane, a good rigid diaphragm. But I don't have a sheet. I've got one plank. I'm going to put that one plank right in the center. Now, this is where the connections are important. If I take this plank, which is going to be green, because green is the color of planks, The plank goes on top of both boards like a deck plank. Think of this for you're doing your deck, right? So these are the deck joists. You put this deck plank on top. A deck is a diaphragm. Even though all these deck planks are disconnected, it acts as a diaphragm. This is why. Well, assuming you connect it properly, it does. All right. So in case A, we're going to install all of our deck planks with one screw in the center of the deck plank on one joist. And the same thing here. Now remember, what we're trying to avoid is this tipping racking action. And the shape change that would happen between this and this, if the planks weren't, if this sheet wasn't here, it would look like this. Oh, wow, that's a curvy curve. So that's a straight line. Oh, I rubbed the microphone. Okay, it would look like a parallelogram, like that. So we're trying to avoid that shape change. So let me make this even easier, actually. Put my plank on the bottom of these, just so it's clear what's going on. Okay, so we got the same blocks, but this time we're putting the plank on the bottom. We're still going to only install it with one screw. But now it's down here. Doesn't really matter where it is. That's the secret. Okay, so, but now it's easier to visualize. If somebody were to come over here and push on this, presuming there's no friction between the plank and the board, that when you clamped it with a screw, it's kind of squeezing them together. Neglecting friction, so the friction's not going to twist. Like this is a Teflon plank, and these are Teflon joists. They slide very easily past each other. Okay, you put one screw in here, what's going to happen? Well, it's going to pivot because nothing's resisting this. All you've done is you've taken a stick and a pivot point, and it's just going to rotate. It's going to rotate about that point, and so is the other one. Okay, they're both going to rotate over. You didn't solve any problems. Well, I thought you said that if you had used the planks on the studs, then you can get the extra, extra strength. Well, that's true, but you have to connect it properly. Otherwise, you don't get any strength at all. So let me show you how. That way you know, and you won't accidentally make a house that falls over. Okay? So I take the same two blocks. And my deck plank, I'm going to draw a little wider for clarity. All right, now instead of putting one screw in the center of the plank, I'm going to put two screws in one end of the plank, and I'm going to space them apart from each other. One there, one there. Now, I know everybody watching this loves force diagrams, and that's why I'm going to show you one. Here's what happens, okay? Something tries to push this over. First question is it going to try to rotate? The answer is yes, it will try to rotate unless something resists it. So is it going to try to spin around that point and that one's going to resist it? Maybe. Is it going to try to spin around that point and that one's going to resist it? Maybe. It's the same math. It doesn't really matter. But for simplicity's sake, let's just use the middle one as a rotation point, okay? So this force is trying to make that member rotate around that point. It's trying to do this, which means for us to make it not move, we need to make it do that. We got to push back the other way. Well, this something outside this thing is pushing it that way, so we can't really, nothing's helping us up here. And nothing's helping us on the pivot point because we have no friction, and that's just one rotating hinge point. But look, we have a fastener down here. There is a screw that's going to go through the deck plank and then through the joist, and that's going to generate a shear connection, right? So if I have this hand and this hand, I luckily have both, and I do this, I can slide them right past each other all day long, okay? There's no shear strength here. But if I took a nail and I nailed my hands together, they wouldn't want to do this. They wouldn't slide past each other because I got shear going on. An example being this marker. If I put the marker between my hands like this, I can't really slide one hand past the other because this thing is in the way and it's basically bonding my hands together. Okay, that's what the nail is doing now, or the screw. So I got the screw down here and it's keeping one thing from moving, which means it's given me some resistance to motion here. there's some force I can apply here. Let's see. So if that's pushing that way, this is going to push it this way to resist it. So here's the force diagram. You know, we draw force diagrams to simplify things and make it easier to understand what's going on. So if I simplify this board into a line, it's a simple line. I got a force on the top. I have a pivoting point in the middle. And now I've got a force from the bottom resisting the force from the top. So, you know, the math being what it is, the math could be all kinds of things, right? So this distance to the center matters, and that distance matters, right? If that distance is huge and these are the same force, then I'm going to be able to turn this with the top one, right? If these distances are the same and the forces are the same, then this will not rotate, right? Because moments are forces times distance. You first equation. I know. I won't do too much math. But right, so that's the premise that's going on here. When you break this down to the roots, that's what's going on. So, when we go back to our deck plank, what we can do is we can associate strength from the plank to the stud. So we say, because we installed this one plank and it's got this fastener and this fastener, and they are some distance apart, and we know the size of the wall, we know the size of everything, we know we got 10 planks going up the wall, whatever, right? You can just multiply the numbers out and multiply by the number of studs. Like obviously you've got some over here too, right? Those are contributing. So what's happening is each one of these is like kind of insignificant. It's a little strong, but not like, you know, if you had two hands and they were pretty close together, you could probably twist them and like break it or something. But when you add up, you know, the 1,000 screws you put in a deck, each one of these things is going to contribute a small resistance to twisting. And that resistance to twisting is the resistance that the sheet could also give the deck. So that is why planks can still do the same thing the sheets can. Pretty cool, huh? Right? So diaphragm doesn't necessarily mean flat sheet good, but it does mean that it's a system of surfaces or blocks if you put them in the wall, right? And all that stuff. But you know, you can do planks, do sheet goods. It don't matter. It don't matter. Okay. So that is something else that you now know about sheet goods and diaphragms. All right. So we kind of talked about, you know, where they come from, what they do. So, you know, what kinds of diaphragms are there, right? There's the floor, the ceiling, and the roof. Well, the roof's only slightly more complicated because it's at an angle. It's pitched. And there's two of them usually, right? In a simple house, which people don't really build. There are two roof diaphragms. There's that one, and there's that one. They're doing the same thing. They're just at an angle, right? And that's that, right? And then there's of course the ceiling diaphragm. So here's another neat idea. Okay, last one. So ceiling diaphragms. If I had a beam, everything starts out with a beam. I had a beam. Okay. What if I had a regular sized beam with a regular load? It would do something. What if I took the beam and I made it skinnier? Under the same load, would probably do something too, but it would probably not be as strong and it might deflect more. Or it might even, you know, break. That'd be sad. But that could happen. Now, what if I went the other direction? What if I took a big, chunky beam and I put the same load on it, right? That'd be pretty stiff and strong, wouldn't it be? Okay. So, big, fat, chunky beam. What if, let's look at the top view, right? So right now, all these are like side views of our beams. We're going to look down from the top. What would that look like if we looked down from the top of the beam? Okay. Let's presume the beam is, that wide and it's got these big blocks below it that we are drawing here, right? This is the top down view. That's a regular-ish beam width, okay? What if we took the beam and we made it thin? Thin. Same blocks, same load, okay? If we made it thin, it'd probably be less strong, Probably kind of floppy. What if we just took that and instead of being like a thickness like an inch or anything, what if we just made like half an inch? It's like it's just that. Yeah. Top down view. It's just a thin little sheet. Yeah. Maybe like some OSB or plywood or something, right? It'd be pretty bendy, right? As soon as you try to top load it, it'd probably like bleh, or like boo, or it just like it'd be too floppy. It couldn't hold much weight doing that by itself. But what if we took that little thin beam and what if we like added something to it, made it a little stronger? What if we took like a bunch of blocks or something that were all connected to each other, right? So they're all connected to each other, let's say like at the bottom or the top or whatever, because like this is a top-down view, right? So let me draw a front view again. This is the front view of our thin beam. Okay, we got the blocks on the side, and we have our beam that looks like this, because it's still the same size. It's just thin, right? And we're going to add these blocks that go all the way down like that. Yeah. And then we're going to connect them all together with one big long piece of wood and one big piece of wood. What if we did that? Well, it'd probably get stronger, wouldn't it? Because now it's not going to be flimsy bendy because it's got these bigger blocks that are kind of giving it its stiffness again. That's pretty cool. What if we took this beam and we made it really tall, but kept it really thin? All right, so let's keep the thin part with the blocks and just make it really tall. Super tall. Okay. And now we've got, I'm drawing one line for each block because that's just less work. Okay. Now we got that. Well, that's a cool beam, right? Yeah. You know what we just made? I bet you know what we just made. We just made a ceiling diaphragm right there. That's all it is. It's a flat, deep, thin, blocked, nailed beam. Everything's a beam when you think about it. Man, that blew my mind when I learned that. So that is what these diaphragms do. So it's like, well, okay, so if this is the ceiling, now we're looking top down. Boom, there's a bunch of ceiling joists. Cool. So what are these like posts? What are the things like that? Let's say there's no posts here because there's no like sideways posts in a house. Okay. So instead, when something's pushing the ceiling diaphragm this way, what on earth is resisting it? Well, instead of a post at the bottom of the beam supporting just, contact, it's connected, right? What if we set our ceiling on some walls? There's a wall below that one and a wall below that one. Okay. Now the ceiling is sitting on walls, and not only is it sitting on walls, but we're going to nail that ceiling joist down to the top plate of the wall so it can't go anywhere. And you know what? Speaking of ceiling joists, if you were framing a room like this, you wouldn't put a ceiling joist on the wall. That'd be dumb. You don't put ceiling joist on walls because the whole point of a ceiling joist is to support weight spanning from wall to wall. If it's got a wall there, you don't need a ceiling joist. So if I had a room and that room was a box, and if I had another color, which I do, and that color was green, and the green were ceiling joists, and the ceiling joists were happy. All right, that's where I'd put my ceiling joists. So it's like, well, then you're saying, well, okay, I've got a red wall over here, and I got a red wall over here, but I didn't put any ceiling joists in. So how the heck am I supposed to connect my diaphragm that's supposed to be here to my walls? Because the walls are the only thing that I don't have posts. Well, the secret is the diaphragm. That's the secret. I know. So it's just so cool. Now, let me give you a little cross section here if you're not super familiar with framing. Okay, cross section of this thing is going to be in black because that's easier to see in honor of our whiteboard named Deshaun. So we're going to have 2 top plates in wall framing, and then there's your stud. This is the cross section. Usually like here at the ceiling joist thing. So you've got a ceiling joist floating over here, going in and out of the board, right? But none over here. Well, what you're typically going to do is your sheetrock ceiling goes like that, right? It's connected to all the ceiling joists. Well, you don't want to leave it hanging over here. So what you're going to do is you're going to take a block of wood, usually 2x4, 2x6, like that. X means cross section. Yeah. And you're going to lay it flat on your wall. You're going to screw it or nail it down right here to the wall, connect it. And then guess what you're going to do? You're going to take sheetrock screws and you're going to screw it in all the way down the sheetrock board, all the way down the wall. And the diaphragm, being a system of components, is going to be sharing load between all of the sheetrock pieces and all the nails and all the wood connected. And that's why you stagger seams and stuff, right? It's going to share that load all the way out to the edge of the sheetrock, where that load will be transferred through the sheetrock screws and collected into these other pieces of wood, which will then transfer that load through the nails back into the top plates in the wall. And the top plates in the wall are the things that are resisting the diaphragm from moving. So I've approached this from multiple angles. Hopefully diaphragms are somewhat cooler to you now. But this is just like a thing that's happening in your house where, and you may wonder yourself, like, why is it that important that I connect this here and connect this here? Well, everything is connected the way it is and the code is the way it is because everything's designed to work together in a super specific way so that when crap happens, you don't die. So don't question why, somebody says, yo, your nail pattern's here missing, or you've missed these nails. Or it's like, well, it's not falling over, is it? Well, no, but things got to work, things got to work. So that is diaphragms. That is the secret. We have our lovely new whiteboard named Deshaun. Oh, I hope that was as thoroughly enjoyable for you guys as it was for me. I think it's time to end it. Thank you for watching. Wow. Yes, indeed. I did indeed that thumbnail with the wrong name. That's something to fix for next time.